Okay, so now at last we're ready to apply those rules of limits to a difference quotient. Okay, so that's what we're after. We want to find dy dx. We want to find a derivative, the generalization of a slope that applies to nonlinear functions. We're going to do it by taking the limit as delta x goes to 0 of the difference quotient, rise over run, delta y over delta x. So good, we're all ready to go. I'm looking at that delta y over delta x, and I've got the delta x in the denominator. Okay, fine, that's in the denominator. That's an issue, but we can manage it. But the bigger thing is I'm not seeing the two things I need the way it's written right now. Okay, I'm not seeing the specific function. Okay, I'm just seeing this delta y, and I'm not in the numerator, I'm not seeing delta x. Okay, so delta x in the numerator. So let's remind ourselves of what we're talking about when we're talking about delta y. So delta y, what was that? That was y1 minus y0. All right, that's f of x1 minus f of x0. Okay, so that's how I'm going to get the specific function I'm interested in. Like if I'm going to be interested later on in the derivative of y equals x squared, this is how I'm going to get that into my expression that I'll take the limit of. Okay, so far so good. Let's incorporate that and rewrite dy dx. Still the limit is delta x goes to 0 of f of x minus f of x0 over delta x. So it's an improvement, but I'm still not seeing my delta x up here in the numerator, up here in the part where I'm putting the information about the specific function. And that's bad because delta x is my real variable here. Delta x is playing the role that in the past lesson we were just letting a generic x play. Delta x is the thing that is actually moving and varying as we're going toward the limiting value. So I'd really like to have that delta x up here so I could see what's happening as it's getting smaller and smaller, what's happening to those f's. Well, delta x is sort of lurking here in the relationship between x1 and x0. So let's see if we can do something with that. Remember, what is delta x? Delta x is just x1 minus x0. Okay, so maybe what we could just say is that x1 is delta x plus x. And that is indeed what we're going to do. Okay, we are going to rewrite this as rewrite delta y in this way that if we weren't going to take the limit of a difference quotient, we'd never do it, but it's going to be helpful for our purposes for letting delta x go to 0. It's the limit of f of x0 plus delta x minus f of x0 divided by delta x. Okay. And this is indeed how we write the difference quotient anytime we want to take its limit. We always express the delta y as the function evaluated at the starting point plus the delta x minus, the starting point plus delta x minus just the starting point. And that is our delta y. Okay. And the reason why we're doing that is that that incorporates both the function that we're interested in and delta x. So it's the right way to do it if we're taking a limit based on the behavior of delta x becoming really, really small. Okay, the other thing I'm going to do, you can choose to do it in your notes or not. I'm going to just sort of observe here that this has also kind of got a lot going on in it. There's subscripts and deltas and all sorts of things. Now that I've got it written as x0 plus delta x, I really don't need that x0 anymore. I don't need that subscript. There's only one x here. So just for my own sanity, to reduce the chance of other mistakes. I'm going to erase that x0 there and there. Put my x's back. Okay, it just makes it a little bit simpler. But I'm going to remember here again that in this context, delta x is really what's moving. Our x here weirdly is kind of like a parameter. All right, so that's the general form for taking the limit of a difference quotient. Let's do it for a couple. Let's do a couple of examples here. And so let's first start with an example that is awfully easy. Okay, so let's start with f of x equals 2x. Let's take the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. Okay, so now I'm going to substitute what f of x is. It's 2x. Okay, so f of x plus delta x is 2 times x plus delta x minus f of x is 2x. Okay, see what I've done? I've just taken this particular function and I've put x plus delta x in for x, and I've put x in for x. And now I'm dividing that by delta x and just sorting out the top there. Actually, let me do one other thing here. When I rewrote that, I lost my limit and I still haven't taken the limits yet. So I'm taking the limit as delta x goes to 0 of that whole thing. And down here, I'm also taking the limit as delta x goes to 0 of, now I'm going to do what I started to do, which is just distribute this 2x plus 2 delta x minus 2x over delta x. That is still the limit as delta x goes to 0. The 2x's cancel. I get 2 delta x over delta x. Now I can do my little trick. Every place except where delta x equals 0, I can cancel that. That is the limit as delta x goes to 0 of 2. That is 2, and that is indeed our answer. Okay. Well, you might not be super impressed. We didn't need calculus to find the slope of a linear function, and 2x is a linear function. It has a slope 2. Good that we got the right answer, but we really didn't need to take limits to find that. So that was kind of a trial run, so to speak, and let's do a real example. Yeah. So now for our second example, the one I promised, we'll have f of x equal x squared. So same as before, taking the limit as delta x goes to 0 of x, f of x plus delta x. What I'm doing now, I'm applying f to x plus delta x by squaring it, minus x squared. So I've got my, this is my y1 value, my ending value, and this is my y0 value, my starting value here. It's my delta y, the whole thing in the numerator, and delta x in the denominator. Just as before, I'm going to do some algebra now on that numerator to simplify it. So that is x squared plus 2x times delta x plus delta x squared minus x squared. And once again, I've left my limit sign out there, but it belongs there. The limit as x goes to 0. That whole thing divided by delta x. I just want to make a comment on what I'm doing here when I'm squaring this thing. I'm ignoring the fact that x and delta x have this relationship with each other, and that delta x, like I know things about it. I don't need to know anything about it for the algebra part except that it's a number. So this could just be a plus b squared. I'm doing the algebra the same way here. Okay, so having done that, once again, I can cancel this x squared here with that, and I'm left with limit as delta x goes to 0 of 2x delta x plus delta x squared, and I should have had a squared there. Okay, so when I was multiplying out this square, I get the first term squared, the 2 times the product of the first and last term, and then the last term squared there. So that was just a mistake to have left out the square. Here it is. I canceled these terms, and now I'm just rewriting it this way. So again, same trick as before. As long as delta x doesn't equal 0, I can divide it out. That is the limit as delta x goes to 0 of 2x plus delta x. And the limit of that as delta x is going to 0. Now I'm dropping the, let's take the limit instruction because I really am taking the limit now. That is just 2x. As delta x goes to 0, 2x stays at whatever it's at. X is just kind of a parameter here. Delta x is going to 0 because it's going to 0. And what we are left with is 2x. And that is indeed the derivative of this function. Yeah, that was a dumb way to write it. The derivative of the function we started with. Using my other notation, it is I keep writing the y when I want to write the function. Let's take the derivative with respect to x of x squared, and you get 2x. This is what we found. Okay. All right, so that is in fact the derivative of x squared, and will always be the derivative of x squared. Let's think about what we got from this. So one thing that we were expecting is we were expecting the derivative to itself be a function of x, and indeed it is. Okay, the derivative has an x in there, so that means we can substitute different values of x. So if we want to take that derivative and evaluate it at 3, it's going to be 2x, that would be 6. F prime of -5 would be -10. So we could put in numbers into the derivative function and get values for the slope of the original function. So in saying that the derivative of f at 3 is 6, what we're saying is that the slope of x squared at the point x equals 3 is a slope of 6. At the point x equals -5, the original function, y equals x squared, has a slope of -10. Let's think about what y equals x squared looks like. It's a parabola, trying to make it symmetric here, not too bad. Here's my y equals x squared. That's about what the graph looks like here. And the in saying that dy dx equals 2x, let's think about what that means. It means that as I was saying, if we pick a point here and want to know what the slope is, if that point is x, slope of that line is 2x. The functional value is x squared. Just as with slopes, remember one of the things we're always worried about with slopes is it positive or negative? Positive slope means the function is an increasing function. It means that the impact of x on y is a positive one. Same story with derivatives. Okay, so the Derivative being greater than 0 means y increases as x increases. And right over here, dy dx less than 0 means that y decreases as x increases. Okay, well, 2x, that derivative for the specific function dy dx equals 2x, that is greater than 0 and x. So there, and x is greater than 0, and that derivative 2x, which is the derivative, is less than 0, and x is less than 0. And we totally see that in the picture, okay? This function is decreasing here when x has a negative value and increasing when x has a positive value. The function itself, f of x, always has positive values. It's a square, after all. It can't be negative, and we see that too. All the y values are above the x-axis. They're all in this positive range here. So the function itself always has positive values. The derivative has positive values where the function is increasing and negative values where it's decreasing. Okay, so in the workshop, you're going to use the same process, take the limit of a difference quotient to find the derivative of another function, and that's kind of designed to help you wrap your brain around the process. But going forward, we don't take limits every time we find derivatives, okay? That would be reinventing the wheel. These limits have been taken, we know what they are. They are codified in a set of rules for derivatives, and we'll be going through those rules in the next unit. So I'll see you then.